Now, we have our first equation in this course. Wavelength times frequency is equal to the speed of light. Now, I want to point out that you can walk around an equation and look at it several different ways. And this is something that you probably want to get into the habit of doing anytime anyone says, here's an equation. It's useful. Know it. It's not just math. This is the kind of symbolic math kind of view of it. Now, when you write that down, you ought to be able to point to everything that is in that equation and say what it is. Lambda is the wavelength. Frequency is the Greek letter nu. And c is the speed. You also ought to be able to point at those things and say, what are some reasonable units to put them in? If I'm using SI units, and I almost always am using SI units, the wavelength needs to be in meters. The frequency needs to be in hertz, which is the same thing as 1 over seconds. And the speed needs to be in meters per second. And these are all compatible units. So if someone throws a problem at me where I don't have compatible units, I'm going to need to do a unit conversion, like we did in Module 1, before I put it into the equation, or the equation is not going to work. Also, knowing the units will help me detect algebra errors when I solve the equation. One of the things that we did in the last video was solve this equation for frequency. That's get frequency all by itself on one side. And we said you can divide both sides of the equation by wavelength to get an equation for frequency that way. Now, if I did the algebra right, here it's trivial, right? I mean, I know I did it right. But if I had a more complicated equation, I might make an algebra mistake. And I can detect it by checking the units on each side of the equation. The units on this side of the equation should be 1 over seconds. The units on this side of the equation should be what? Speed of light is meters per second. And then the wavelength should be in meters. So the meters will cancel, and that should give me 1 over seconds. So the units are the same on both sides of the equation, so I can be somewhat confident that I got it right. All right, that's the symbolic math view. Here's also an English view, where I say it in English. Wavelength times frequency is speed. Say it just like that. You got to have them both. You can't have one or the other. You can't just have one or the other. Now there's another way to look at this. And that is in terms of what happens when you squeeze one variable. What happens to the other one? For example, what if I cut my wavelength in half? I could replace lambda by lambda over 2 in that equation. Now what do I have to do to the rest of the equation to keep it true? Like, what has to happen to these other things? Now, changing the wavelength does not change the speed. Changing the frequency does not change the speed. Does not. Depend on just wavelength or just frequency. It depends on the product of the two things. So this is pretty much a constant, and the speed of light is a physical constant in a vacuum. It's not going to change whenever the frequency or the wavelength of the light changes. It's still going to be a constant. So it's kind of important to know that that's a constant. And it depends on the medium that you're traveling through. We said that before. Unless you change what you're traveling through, like if you look at the speed of light through vacuum, it's different from the speed of light through air. or you change the kind of wave you've got. I mean, an electromagnetic wave will always have the same speed as the speed of light, but if you have a sound wave, that can be considerably slower. Anyway, that's going to be a constant for the particular medium and type of wave that you've got. So I can't change that C. It's got to stay the same. But what about the frequency then? I'm going to have to change the frequency. I'm going to have frequency in here somewhere. What times the frequency is going to make this all work out? Well, I'm going to have 2 times the frequency, right? Because that way the 2 over 2 will cancel out. So I can say if I double, or if I half the wavelength, you have double the frequency. Now, whenever somebody gives you an equation like this, decide what is constant and what changes. And try to tweak one of the variables and see what happens to the other variable. All right? There's a third way of looking at any equation that people give you, and that is to look at what it would look like on a graph. If you were to make a graph with, let's say, wavelength on that axis and frequency on this axis, what would it look like? You could try taking different wavelengths and frequencies and plotting them on there, and you'd end up with something that looks kind of like this. You'd end up with a graph that looks like that. This is actually another way to show this relationship. You can show it graphically. And this isn't the only way that you could show it graphically. What if you divided both sides of this by nu and looked at this equation? So you're calculating the wavelength. Well, this looks kind of like y equals a slope times x plus an intercept, the equation for a line. What is what here? Y is the wavelength. What's your x? It would be 1 over nu. That would be your x. And what's your y-intercept? 0. And what's your slope? The speed of light. The slope is the speed of light in this graph. So let's draw that graph. I would say this is something that an A student would do. Once you get to that competent level, this kind of graph is something that you would instinctively kind of write down whenever somebody throws an equation. I want to see what this looks like on a graph. My y on the graph is going to be the wavelength. My x on the graph is going to be 1 over frequency. And my y-intercept is going to be 0. And the slope of the line is going to be a constant. It's going to be the speed of light. So what does that do for me? If I look at this graph, it gives me a way to experimentally measure the speed of light. If I collect some wavelength data as my y, and I collect some 1 over frequency data as my x, I can fit a line to this, and the slope of the line is the speed of light. So I can get the speed of light experimentally then, if I can measure these two things independently of each other. So think about that anytime I throw an equation at you. Try to write it down symbolically, name all the variables, write down their units, say the equation in English, play with the equation so that if you double one thing, what happens to something else? Those make great test questions. And if you're an A student, you can go ahead and try and visualize it graphically. try and take a look at it, graphing different pieces of the equation on the x and y axes, and see if you can get some interesting quantity to be the slope on your graph, something like the speed of light. Then this is the basis for an experimental setup for this. And that would be another way to look at the equation. If you have a graph like this, you can set up an experiment to measure things from the graph. And then you're starting to be able to design your own experiments.